Then we're off. Y'all know we're off next week, right? Okay. And then we have this week right here. And then what we'd like to do is try to go ahead and finish up the lectures and then be in lab the rest of the class. Does that sound like that would be the winner? Yeah. Yeah. So that's what we'll try to do. So we got 3 chapters to go. I thought we had 2, but we had 3. But the logic you should do okay, and then we come back in here, and then we'll have our 3rd test on December the 9th, and then we'll have our final exam on the 11th. But we'll let y'all work in lab after the final exam. We'll get the final exam at the start of the class. Test 3 will be doing at the start of class because we need to go over it right real quick and look at that before y'all go into the final. Logic instructions. 13, yeah. And we're all going to also talk about bit shift instructions. These are still available. These are logic instructions, work on words, because our other logic we use regular contacts, right? You understand? So I can get a 3-bit and I can get a 3 input and just by putting 3 normally open contacts in series with each other. So all our logic instructions work on words. Addressing modes, these are the way we address our operands. We have immediate address, and everybody okay with that? So what's immediate address? So we've used this a lot. So if you type a number, if you're doing math and you type a number into source A, that's immediate addressing. So immediate addressing is what we deal with constants, right? You understand? The direct addressing we use, the direct addressing is specified by a data file address that contains the variable. So we would say N17, and N17 means this would be inside the N7 data file, and it would be location 17. It would be word 17 inside that data file, right? Everybody understand that? Okay. This would be indirect addressing, which we haven't used yet. So indirect addressing, the specified data file address contains the address of the variable operand. So if I said N7, if I said N10:1, then it would go into N10:1, and there would be a number inside that data file, and that would be where we actually go. So let me bring up my pencil and give y'all. So if inside N10:1, if it equal to 52, then the address of my operand would be N7:52. So when it sees these brackets, what it does, it goes to this address looking for a number. The number in that address would actually be the data file address that we would go to. So anytime you see these brackets around an address, that means it's using what we call indirect address. You understand? Really? Brad understands. That's inside the address specified. So this is N10:1 has a number in it. And my example was I said it was equal to what? 52. So what would be my address right here? It'd be N7:52. That makes sense? Okay. Yeah. The index address, and this is a new address mode. The address of the operand is specified by the contents of an index register. In some of your PLCs, it's S24. In the MicroLogic 1100, we're going to simulate it. But what we do to specify index addressing is we use the hashtag. We used to call it the number sign, but now we call it the hashtag, right? So if we use this says N7 using index addressing, and this is what we call an offset. So what we would do is it would come over here. So let's say S24 equaled to 5. Then my address of my operand would be N7:8. So what it does, it takes this number, adds it to the contents of S24, not S25, Rich. I don't know where I got 25. I had 5 on my mind, I guess. Adds it to the contents of this, and then this is where it comes up with the actual address of the operand. Now, what's nice about the index register is we have instructions that automatically increments the index register for us. And this is what this bit shift left is going to use in the bit shift right. We can point it to one word, and if you fill up that word, it will automatically take you to the next word. It'll automatically index, it'll automatically increment the context of the index register, and it will let you go through what we call tables and stuff like that. It's really cool. It'll be a little more understanding once we actually show the application of this. So the hashtag indicates what? Index addressing. It's going to take this number, add it to the current contents of the index register, and then the results will be your address of your operand. For some PLCs, the 1100 doesn't technically have a index register, so it simulates it. It simulates it on some of our instructions. But if you were on the 1000, or if you was on that guy over there, the 500 series, you would S24 would be the index register. These micropods does not support index addressing directly. It's simulated. We can still use the hashtag. It's just that we do not have to establish an index register. So the big difference here is S24, I can load it with any number. On MicroLogic, on the 1000, it's assumed to be 0 to start off with. So we can't really load it with a number. It just assumes it to be 0. Are we okay? This makes sense? Some of y'all like those bobblehead dolls, right? You put it in the back of the car. They always do like this. And you have no idea where you're going, but you say, yeah. Yeah. Well, most of them go like this, but yeah. When it Mad Max, they kept a bobblehead doll up on its dashboard. Yeah, it's Hula Girl, yeah. Chris has got a hula. So here, these are going to use these are logic instructions. So we have 3. I mean, we have 4. We have a what, not, and, or an exclusive or. Now, so how would we get an and, an or, and an exclusive or? By combining it with the very first one, the not. Yeah. So what we would do is we'd take the answer of the and then we would not it. So what a not does, and we'll look at that. What do you think the not does? Remember, these guys deal with words, which is 16 bits. Because if I wanted to do it with less than 16 bits, I would do it with contacts, right? You understand? So what would you think the NOT would do on a 16-bit word? Somebody say invert all the bits. So if I can, we'll see that. So if I had this in a data register right here, if I did this and I ran it through a NOT, I would end up with this. This would be my answer. I don't know if I had 16 bits or not. So all the NOT does is just invert all the bits in a word. So let's look at that. We can cascade NOTs and ANDs to get what? Yeah, it's your NANDs, your NORs, and your exclusive ORs. So that gives you all 5 logics. And of course, we're going to do this one. And then we're going to deal with a bit shift left and a bit shift right, which are some pretty neat instructions. And of course, what we'll do here is to see it happen. We have 2 options on the bit shift instructions. We can actually send them to an output, which you'll probably do, or we can actually use the data, monitor the data files, right? You understand that? How to monitor the data files? So how do we monitor a data file? How do I monitor a data file? I just come up here and double click it, and then this allows me to monitor it, right? You understand that? We did this several times. So if I want to see what's actually going on inside my output data file, I can just bring that up. Of course, now any outputs that's true would have a 1 in it. Any outputs that are false would have a 0 in it. So remember, we don't directly access, our PLC program does not directly access inputs, and it does not directly access outputs. What the PLC program does is access these data files. So what happens is when it scans the inputs, if it finds an input true, it'll put a 1 in the data file. And then when it actually runs the program, it does what? It doesn't read the inputs. Your program doesn't read the inputs. Your program does what? Reads the data file for the inputs. That makes sense? And your program doesn't update the outputs. Your program updates the data file for the outputs. And then when your PLC actually goes out and actually changes the outputs to 1s and 0s, it's reading these output data files. And by the way, guys, we can address these data files. Y'all understand that? So if I wanted to make the input go to a certain condition, the outputs go to a certain condition, regardless of the inputs, you can store that into a data file. And one of the things you look at when they, like on the Amatro line, when you hit the reset. Well, when you hit the reset, what it does, it runs a subroutine and just stores stuff in the data output file. And all the outputs go to the original state, right, for a reset, which is pretty neat. So we have access to all these data files. Timers. Timers actually consist of 3 elements, right? Which the book calls registers, but that's not exactly correct. Logic instruction rules. For not instructions, the source cannot use immediate address. Because if you inverted the same number all the time, you would do what? You just use that number. ANDs, ORs, exclusive, or source A and source B cannot both use immediate address. And these are the same rules that we have for our math instructions, right? The destination of all logic instructions cannot be immediate address, and each logic operation is performed on each associated bitwise. Bitwise means bit 0 is going to be, its logic is going to be done with bit 0, 1 with 1, 2 with 2, right? You understand that? Yes or no? NANDs, NORs, and exclusive OR instructions can be created by using a NOT instruction on the destination operand of your other instruction. Are we okay? So these two are new. These top ones, these are basically exactly the same rules. This one, and this one is the same rules. I mean, sorry, rule 2 and rule 1 are the same ones we have for our math instruction. These are the registers that we can perform logic on, the data files. We can perform it on an output, we can perform it on an input, we can perform it on our status registers, we can perform logic on our B files, our timers, counters, and our control registers. We can perform it on a long word, we can do it in messages, and we're not going to look at these, real-time clocks, and these are the addressing modes available to us. Are we okay? So we can use immediate, but not for both operands. We can use direct, right? Or we can use indirect. This did not come out of your book. This came out of the. I need to get rid of this thing. Yeah, these came out of the instruction reference manual that you have access to. These are so it actually, these instructions actually update bits inside your status register, math status register, but there's only two that we have. We have the 0 bit, so this would tell me I could use this to see if the answer to your logic was all your bits turned out to be 0, all 16 of them. And then we have one that indicates the sign bit. And which one is the sign bit on a 16-bit word? No, on the word itself, which one is the sign bit? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is this a positive? Well, actually 15. Because this bit is what? This is bit 0. So bit 15. So what type would this be, negative or positive? This would be, no, negative. If it was positive, that bit right there would be a 0. And he uses something called 2's complement, guys, which is really weird. But you need to understand that if you're going to do binary math. So right now, this bit right here, on that first one, the bit, this would be set. This would be cleared. Why? Is this number equal to 0? No. So what it does is what the 0 bit is going to tell us is if the results of the logic operation, all 16 bits end up to be 0. If it's all 16 bits are not 0, then the 0 flag would be clear. If bit 16 or if bit 15 is set, then the sign bit is going to be set. If bit 15, if bit 15 is 0, then the sign bit will be clear. Everybody understand that? Which one do you think we use most often on logic? Seeing if we get an answer of 0, especially with AND logic. Not, also called the 1's complement. Some people call it an invert. Converts all the bits in the destination operated from a logic 1 to a logic 0 or vice versa. Pretty straightforward, right? Doesn't change your original operand. It's where it's the destination operand that's changed over. The AND generates a logic 0 if the destination operand, whenever in the destination operand, as long as there is 0 in this corresponding bit. So by the way, we call these mask. So if I came over and had this 16-bit number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then I came up here and did this and we call it a mask because literally what I'm doing is I'm covering up bits. So this would be source A. So it's just like the math instructions. This would be the mask. We call these masks because that's what we're doing. We're covering things up, right? This would be in source B. And then my answer, the results, would be put at our what? At our destination. Are we okay? So what would I get? If I AND a 1 and a 0, what do I get? AND means they both, okay. And if I AND a 1 and a 0 and a 1, a 1 and a 1, yeah, a 0 and a 0, 1 1 0 1 1 1 1 0 0 0 0. So what we're doing is we're stripping off these bits right here. So notice when I put a 1 there, this is my original one. When I put a 1 in the mask, and whatever my original one, that's going to be in the answer. If I put a 0 in the mask, it don't make any difference what source A bit is. It's going to come through a 0. That makes sense? And we call this an AND mask, used to make desired bits in the answer. A mask is you cover up. That's what we do. We cover it up. So what I've done, if I come over here and take this same number, so let's redo this. I'm going to come up here and erase this. And instead of writing 1s and 0s, what I'm going to do is in my original one, I'm just going to replace it with an X. An X means it could either be a 1 or a 0. And then down here in my mask, I come down here. This is the mask. I'm going to come up here. Let's say I come over here and do this mask. Well, what would come over in my answer, no matter what this is, it would be what? It'd be a 0. No matter what this is, it would be a 0. No matter what this is, it would be a 0. What this would come through. So if it's a 0, I would see a 0. If it was a 1, I would see a 1. So what I've done is I've masked off these bits right here. So this would be a 0 0 0. That would be an X, right? 0 0 0. That would be an X. 0 0 0. That would be an X. Whatever that happened to be. So what we can do with an AND mask is the bits we don't want to come through. So let's say I had a big number and I wanted to read an input file and I wanted to see if this bit right here was set or cleared. I was just interested in that one bit. I wasn't interested in any more of them. Then what I would do is I would come up with this mask right here. I would go 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0. And what I've just did is I've stripped off all those other bits. Now, how could I tell if that bit was set? Well, what I would do is I would use that 0 flag. After my AND mask, I would use it. I would say, okay, if that 0 flag is set, it means what? It means it was originally a 0. If it's a 1, it means it was originally set. So we can actually tell. We can actually tell using that 0 flag. Y'all understand what I'm saying? So I could come back here and use what? Yeah, well, I could check bit 2 in my status register, right? You understand? We could actually assign that to a contact. So I could come over here and say S0/2, and if it was 0, the contact would be closed. If it was non-0, the contact would be open. So we could assign that I didn't put my 2 up there. So you can examine using that AND mask, or I could say if all these 4 bits are set, you know, if all of them are set, then so that's an AND mask. So what we do with an AND mask is we make sure bits in our answer are 0s, and then we let what? We let the other ones come through. Right? Does that make sense? Everybody okay? Then we got the OR math. The OR math is exactly opposite of an AND. So what an OR math does, it makes sure bits in the answer are ones. The AND math makes bits in the answer 0. An OR math makes sure bits in the answer is 1. No, we let it come through with 0. We don't cut. We no. So let's come up here and do this again. Let's come over and do this. Well, mask would be covered up would be indicated with a 1. Yeah. So this is an OR. What would this be? This would be a 1. No matter what that one is, this would be a 1. This would be a 1. This would be a 1. That would be an X. This right here would be a 1. This would be a 1. This would be a 1. This would be an X. This would be an X. I need to change my color so y'all can see that through my mark. This right here would be a 1. This would be a 1. This would be an X. This would be an X. This would be an X. That would be a 1. So what we do with an OR mask is we make sure that bits in our answers are 1s. And then we let the other bits come through unchanged. So on AND math, we get 0s, right? We can make sure certain bits on our answer are 0s. OR math, we make sure certain bits in our answer is 1s. Inputs or outputs or data files, we just speeds it up. Instead of trying to do all this logic, instead of me coming over here trying to do something like this with 16 contacts, we could do it with 1 instruction. Instead, if they're all closed, right? That makes sense. Or if they're all open. So what we can do is we're dealing with real long numbers, and we can get up. So I could, like I might have 8 contacts. Instead of trying to do that, I could bring my input into, that could be source A. I could bring the input data file into source A, and then I can match it off and make decisions on a bunch of stuff real fast without doing without having to wire all the contacts in series and wire all parallel and stuff like that, which makes it a lot more efficient. So we can do things with one rung. We started with 1 instruction. All these contacts together, right? That makes sense. Because source A can be what? Source A, we can input directly from the input data file. We could bring that in. Then we could mask it off, and then we can use the decision of that. So if they were all 1s, right? That makes sense. Exclusive OR. So exclusive OR, we use these for compare instructions, right? And these are bitwise. So it generates a high if the destination operand when the 2 corresponding bits in the words do not match. It would generate a low if they do match. I mean, this would be easier than trying to figure out those contacts too, wouldn't it? Let me split it up into nibbles so I can do a 16-bit word really. I can't count. all your AND instructions. So this would be source A. That would be my original operand. This would be source B. Source B would contain your mask, usually contain your mask. And then my answer would be our destination. Oops, sorry. And it's bitwise. Y'all understand? So this is going to be exclusive ORed with that. This will be exclusive ORed with that. This will be exclusive ORed with that. That'll be exclusive ORed with that, just like in the ands and the ors. So what would I have right here? Exclusive OR. A 1. What would I have right here? 0, 1, 0, 0, 1, 0, what? 0, right? So y'all got the hang of it, right? So one bit at a time, and that's why they call it bitwise. Oh, y'all want to keep going? So what we have over here? 0, 0, 1, 0, 0, 0, 1, 1. Now, if we took this answer and ran it to a NOT, then we would end up with 2 instructions would give us an exclusive OR, right? Understand that? Source A can be all those data files we talked about. Source A can be all those data files. This could come in from an input port, or from an input data file. Source B could be another input data file, so you could actually AND these things together. Now that wouldn't be much for us because how many inputs do we have on our PLC? How many word inputs do we have on our PLC? On the 1100. What word are we using? So I've got 10 inputs on these things, input 0 through 9, and they're on, so input, right, colon, everything we put would be a 0 right there. Y'all understand that? Okay. So this is what we have. That's the fixed part of this, but this is a modular or hybrid PLC, which means we can do what? We can add modules to it, and they snap onto the side, which is becoming very popular on PLCs, even modular PLCs, instead of having that rack. Very, very popular. This looks like this is out of the textbook. I don't have a figure number on that. So here they're doing D3 files. What address mode are they using? By the way, the NOT doesn't have a source D. What am I doing? There we go. So what address and mode are they using here on all these instructions? Huh. What address and mode are they using on all these instructions? What address and mode are they using on all these instructions? What address and mode are they using on all these instructions? What address and mode are they using on all these instructions? We're using direct address on all the instructions. Source A can do immediate, but source A is immediate. Source B can't be because we don't have a lot on the NOT. We don't have a lot. We don't have a source B. So this is going to take whatever's at B30. It's going to knot it with what we have there, and then it's going to come up and give us an answer. Okay? And because you're inverting just one thing, you're not inverting two things, you're inverting one thing. Right? That makes sense. By the way, this is where you really, really, really need to use hexadecimal instead of decimal. And why is that? Because if you was trying to come up with this mask, you can use decimal if you wanted to. I think I've erased all my masks. So if this was my mask right there, you could come up here and you could convert it to decimal. So how would you convert it to decimal? You'd have to go what? 1, 2, 4, or you could come up here and enter it directly as hexadecimal. You can enter it at binary, but that would be hard too. So all we do is take our mask and split it up in groups of 4s. What would this be right here? No, B's odd. This is guys, y'all really need to learn this in PLCs. You really need to learn this, especially when it gets to mask. This is the A. What's this? 13, which is a what? D. 5B. Okay. So how do we enter hexadecimal into our numbers instead of entering a binary? I mean, instead of entering decimal. We've already lectured on this. So right here, I'm going to come over here and find my logic instruction. We'll just change it right here, right? Okay. Ain't that neat? So change instructions is just by doing what? Yeah, you just come up here, right up here, and you type whatever instruction you want. Right. So if you wanted to change this to a contact, examine if closed, it does what? Ain't that cool? Now this one's a little different because it don't have the name. On this one, you would have to come up here and change instruction type, and then you just type. But you got to know the 3-digit mnemonic, right? That identifies it. So let's say I come over here and I get this from input, an input 0. We'd bring the whole input in, and then I wanted to come up with a mask. Well, I could come up here and I could take this binary number right here and I could convert it to decimal. And it, by default, your PLC is going to assume the number is decimal. So if you come up here and put AD5B, you'll probably get an error. So I want to enter this in hex because it'd be so much. I'm going to put A, B, what was it, 5D, I think. And then what I'm going to do is I'm going to put an H out there and enter. And it did what? It changed it for me. Now that is the mask, right? You understand that? That is the mask, and it's what I can't. It assumed it's negative, but the mask is correct. So it's best to do what? Yeah, change the hex. And you could do binary. How would you do binary? Yeah, you'd enter it with a B. If you wanted to do octal, you would enter it with what? An O, yeah. And you enter it with an O, and then it'll automatically convert it to the decimal. It'll display it in decimal, but the mask is actually the 1s and 0s. Okay, you understand that? So that's the best way to do your mask, because I'd had to convert that over and get 2003 and 30 when I could have just entered it directly in hexadecimal, right? Or binary. Hexadecimal is the easiest because so those patterns, guys, it's just and what I talk about is you know when you learn multiplication, y'all know multiplication is repetitive addition, right? So you could get the same answer if you multiplied 5 times 5, as you said 5 plus 5 plus 5 plus 5. But what we do is we learn those multiplication tables to make that repetitive math, that repetitive math easy. And how far did y'all have to go in elementary school on your multiplication tables? 12. Here you got 16 combinations to recognize. You got 16 binary combinations to learn. And once you learn those 16 combinations, you can go between these bases without even thinking about it. And we looked at that. Okay. So these are all using address. What I would do if I wanted to get an and is I would do what? Is I would come over here maybe in the next rung right after my and come over here and put another rung. I'm not going to come over. But then I would do what? I would not, and I would not this address right here. B3 colon 4. And then the answer of the not would be my what? Would be my nan. Not the and, but the not. And these are this is just the input file, so you can actually see what's going on, right? You can directly look at these data files and see exactly what's in them, right? And how do you do that? Just go over and double click on it, and this will bring those data files up for you, right? And show you the contents, every one of them. Oh, that's the status. Binary. Here's your timers. Now, timers, these are done in what they call elements. So timers, we have the accumulator and the preset register. These are 16-bit registers. The time base is just a time base. And then these up here would be the flags. The flags would be the status. So every time you set up a timer, it actually comes up and adds its own status bits inside there. So what's this going to do? This is source A. Then source B, this would be the mask. And what address and mode am I using for the mask? What address and mode am I using for the mask? Huh? What address and mode am I using for the mask? Is that the number or is that an address? Is 2030, is that a number? That is not an address. An address is going to start off with something like N7, right? You understand, and then we'll specify. This is the immediate address. That is the number. That is the mask. So my first one, I'm using what address and mode? What source A? What address and mode is source A? That's direct. Source B is immediate. And then my destination cannot be immediate, right? You understand that? So on y'all's test, I'm going to put what address and mode is this, and then one of the answers is going to be hexadecimal. You'll see how many people check the hexadecimal. So all in on RS Logic 500, addresses always start with a data file number, right? Unknown type. I don't know what that is. Oh, Let's see if it gives us any errors. But word level, so I got to specify this to the word level. So what do I need to specify that as a word? As a word. How do I get a word on the calendar? So much to know, right? So how do we specify a word? Yeah, Doc did.
We have little half horsepower motors up here, three-phase motors up here. Half horsepower motors.
So bit shift left and bit shift right, often used to control display signs, flashing arrows showing one lane closed. Using can be constructed with the shift instructions. We have two sequence starts motors. That's my last name. So I know all y'all seen these flashing signs like on the back of trucks when they're working on the interstate, and the lanes move across, and you have these rotating signs where the lights move around them. And we can do that with these instructions. Index addressing, all these guys use indexed addressing or simulate indexed addressing. And while we'll do that, I'll show you that in a minute. On the SLC, on the SLC 500s, the index register would be S24. And also this would be the same on the Micrologic 1000. On the other most advanced PLCs, they don't directly support index addressing, but we can simulate it. Okay, that makes sense. Everybody okay so far? And we'll show you why. So how do we specify index addressing? You know, it's a hashtag. And normally what index addressing does is we have an index register. On the 5000 series, it's S24. It says S2, but it's just like we've only got one status register. So our inputs are actually this right here. It's data file 0, right? And input's data file 0. Let me look real quick. Inputs are data file 1. Yeah, so outputs are data file 0, inputs are data file 1. So technically, when we enter these addresses, we don't have to specify the data file because it's understood. These are fixed, right? You understand that? So, and you won't get an error if you come up here. Where am I at? There. You won't get an error if you come up and do this, but it's understood. We've only got one status register. It's in data file 2, but since we've only got one, you don't have to specify the 2. So the way we would address is this is S24. That makes sense? Okay. Now what we would do in true index addressing is inside S24, we would have a number, let's say 15. And then in my index addressing here, I would say index addressing, then I'd say 53. And what it would do to come up with the address, it would take this number and add it to that. And my address of my operand would actually be B3:68. That would be the actual address. Everybody understand that? And what's nice about the index register is we can increment it or decrement it, and the PLC will automatically do this for us. So what it'll do is it'll automatically go through a range of addresses for us. Are we okay? This makes sense? Yeah, we'll see how it makes sense on test, right? Index addressing is primarily used to scan through tables. When the bit shift left or bit shift right instruction is used, index addressing allows shifts of more than 16 bits because the processor can automatically increment the index register to point to the next word address. which is really neat. So we'll show y'all some 32-bit shifts, which do 4-bit shifts. It depends on how many data files you have. Are we okay? I'm going back. Oops, I'm sorry. Since we only have 10 inputs and 6 outputs on this PLC, we're going to simulate this with RS Pro. We simulate the 500 series PLC. So this simulation, we have 3 inputs, 16-bit inputs, and 3 16-bit outputs. My 16-bit inputs are in slot 1, slot 3, and slot 5. My 16-bit outputs are in slot 2, slot 4, and slot 6. These inputs are hooked up to some BCD switches, and we'll look at what's going on with this later on. So BCD means they only go from what? 0 through 9, right? Okay. Yeah, BCD. What does BCD stand for? Yeah. So those guys are giving me BCD outputs, which means we're sacrificing 6 combinations, right? So binary code decimal is not a weighted numbering system. Math in my PLC, we're going to do math on a weighted numbering system, right? So we'll see later on how we can convert these. So what we're going to do is we're going to be just left, and we're going to get using what addressing mode? Can y'all see that? Next. Right. And what we're going to do is we're going to, we need to go cover a little more information. So what, look in the center of the bit shift left. We start off with the file we're going to shift. Then we use the R6 data file. What's the R6 data file? What's it called? Have we talked about that one yet? This is the first time we've ever used that. This is called the control data file. And so basically it's like a flag register. It's got flags in it. But this is going to be external. And then the length. So this would be how many bits we want to shift. Everybody understand that? And this is where my information is coming from. Okay. And we'll just have to see this work. So let's see what this control register is going to give us, or this control data file is going to give us. When energized, shift the bits to the left. Every rung follows the true transition. The control register R6 must be used to hold the status files, the status bit for the shift left. So this is another status register that we have available to us. Information about the bit shift instruction is this is called a control register. So your book calls it the control. Your book calls it a control register, when actually it's technically called a control data file. It's not a register, it's a data file. The book misuses the term register a lot. And that's where these PowerPoints came from, and I hadn't changed a bunch of them. But the R6 register is actually, the book calls it a register, but it's actually a data file. So if we come over here, let's see here. Oops. So here's the R6, and they call it what? Control. So it's the control data file. Now, if I come up and look at it, it's nothing but flags. So there's single bit flags that we can address. So we got, this is the link, this is the position, we'll have to look up these. Basically, the shift left uses these three right here. Up through? Can I go ahead and talk? Okay. You already know this? Okay. So this is the R6, and this is actually a data file. This is nowhere near. So these data files up here, this is inside, these are actually registers up there. Processor status. This is not technically a register. This is just a data file out there that it keeps up. It treats like a flag register, right? You understand that? So the bit we're going to be interested in is this bit right here. So what happens is when we shift out the last bit, then what happens is that it unloads. When it shifts out the last bit, no matter what length you specify. So here, what they're doing in this program, I don't know where this is at in your book. I need to go back and so this is using R6, right, which is control register data file, word 0, and it's using what we call the unload bit to come up here and reset these files. Which the reset is going to reset it back to what? 0. So we're going to start off moving A into the, so let's put this one in there and let's actually see it work. Now here, it don't make any difference which PLC you choose. And let me get rid of this so we can get our project file back up. So we use what? Y'all found this in the book? Is it in the book? Okay. So this is an input. Which one are we using? Which one are we using in the book? I don't have the picture up. But we have an input, right, on the left hand side. I need the address. I can't give it a name until I get it. What's the input number? It can't be 0. 1, might be 1/0. Is that right? And then what do they call it? Yeah. And then over here we have a what instruction? Move instruction. Yeah, this one we can't do that trick we did before. And we're moving what? All right. And where are we putting this at? Using index addressing. Okay. And then in our next rung, I think we have another contact, right? What's the name? What's that? Oh, it's just a name. And then over here we have the bit shift instructions. Bit shift left. Okay. And what's the file we're shifting? Okay, which is the one above, right? Okay, and then our control is going to be R6 on 0. And then our bit address, where's the bit coming from? Okay. And what's the length? 7. Let's just do this one right now. We won't go any further. So we'll download it. We'll switch to run. Okay. And then as soon as I come over here and do that, then when we come over here and look at this B3 file, can you see what it went to? Okay, we can do that here. So here's the B3 file. You see what it went to? Went to AAAA, right? Everybody okay? Okay. And then I'm going to come up here and I wonder, let me change that. Okay, we're going to press this. Let's see what happens. This is switch 1, right? Nothing happened. Yeah, my computer's trying to do updates or something. Can you see what happened? Yes. Can you see what happened? No, watch this bit. Just watch this bit right here. Don't watch anymore. Watch this bit. Right now it's a 1 in bit what? 4. I'm going to hit it once and it shifted to what? Bit 5. But what if you notice that all the bits are doing what? Shifted to the left. Now, if I come over here and look at this register right here, R6, if I can get it to come up. I'm sorry, we can do it over here. This set here is what we call the unload bit. So what happens is when it shifts out, if it's a 0, so if I do a shift and then a 0 should come in next, right? It's supposed to. The unload went to a what? A 0. Then the next time I do it, it should go to a 1. So every time it shifts out from the most significant bit, it comes over here and goes into the unload bit, which means we can use that, by the way. Well, we're going to show you how we can make it constantly rotate around and around and around and around. So show you how we can make an error. If I had an error where it would go like this and then go back to 0 and go back like that. Sequence starting motors, where we could instead of using AAAA, I could have come over here, and instead of sending it here, then I could have done what? I could have sent it to an output port. But this is what's neat, guys. Let me show y'all this. So what I'm going to do is I'm going to come up here and let's go offline. And instead of doing 7 bits, let's say I do 32 bits. Well, the problem is that this PLC works with words, right? You understand? You know, that makes sense. So what we'll do here is we'll come over here and let's bring up the bit file again. And I'm going to leave it. We're going to go to download and go back to program. And then I'll bring up the bit file again. We'll hit switch 1 again, and he loaded it with AAAA. Notice this guy here's got what? It's got zeros in it. Now let's come up here and hit switch 1. And can you see what it automatically did? But bit 1 changed to a 1. Now how did it do that? Well, that index addressing allows it to automatically go to the next address for us. So I could come up here and I could do a 64-bit shift. So we'll do a 64-bit shift. And this is what index addressing allows us to do. It allows us to go past the length that we specify, right? Okay. So let's start it over again. So loads it. This is wait. Oh. And then when we shift it, yeah, I didn't clear out that other bit. But watch, I keep shifting. Yeah, but watch what what it does now when it gets here. Since I specified index addressing, it can do what? It can automatically move to the next one. See, so it automatically goes down to the next one. And then when I exceed this, what will it do? It automatically go down to the next one because what length did I specify? Yeah, but what it's doing is it's going. So we started off with bit 0, right? Okay. By the way, we need to. Well, what it's doing, it's automatically going to the next. It's automatically going to the next word. Y'all understand that? So it automatically, and this is the advantage of using index addressing, is you can specify multiple words instead of one word. And once you do this one, it automatically goes down to the next word. It automatically increments the index register and goes down to the next word. And it's going to do it up to 64 bits. Now, how can it automatically go to the next word? How can it automatically go to the next word? Sometimes I think I'm talking to myself up here. How does it automatically go to the next word? Because we're using what addressing mode? Index addressing. So this is what index addressing does for us. These instructions can automatically increment to the next word for us, right? So if I go past 16 bits, it will automatically go to the what? It will automatically go to the next word for us. So how many bits could you roll away? You could ship this thing all the way through 255 words if you wanted to. You could do that. And what would happen instead of using this guy right here, let's say right here, let's go to so let's go offline. And let's use output code. Let's use output colon. What's our first output? Output colon 2. And then B3 will, so let's see what happens here. So we'll download it and we'll do this. Okay. And so when I press, I'm online, and when I press this button right here, notice what happened. It did what? Whatever I sent out there went over to the output port, right? Okay. We need to do this too. Oh, this is where the bit's coming from, right? I don't think it's going to let you use index address in there. Sorry, I know what's going on. There we go. If you want to charge your phone, I want you to charge it over there. I don't want you to run this power cord all the way across the restaurant, all across the room, so somebody can trip on it, if you don't mind. So you can charge your phone over there. Huh? Okay, so here what we're doing is we're shifting a what? An output port, right? Can you see what's happening? Okay, y'all understand that? Now, shift left goes from, yeah. Can you see what it did? What do you mean skipping? Well, it shifted a 0 in from the from the left hand side, right? Because you couldn't see the bit files. Now eventually it's going to move over here and start doing something weird. Oh, I'm sorry. That was the bit length, right? So what you got to understand is that if these were motors, they would actually be doing what? They'd actually be following this output. We're doing AAAA. We could come over here and yeah. So I could come up here and load this with a 1. So let's show you another way we can do this. Oh, okay. Oh, I got to change it up here. And what we'll do is we'll change this into a switch, or we can do it. Let's see if this works. No, that ain't gonna work. Now, how would we make it go back the other way? I got to do it quite a few times to get it to move over because it's going down this guy right now. Well, here we're using a bit shift left, shift right. Now, which bit is the unload bit? Oh, yeah, no, 0. Then we'd put like unload, right? Because we don't have to know the address. Oh, see, no, that didn't do what I expected it to do. What I expected it to do, if I put a 1 in RF in this guy, I expected it to come in and do the same thing. So, oh, I'm sorry. This is using the S4 register. And what's the S4 register? There's so much to know, right? So it's actually S2, but the 2 is understood. And we're going to use word 4. So this is actually, are we online? No, let's see. S, S. So what we're doing is we're dealing with this guy right here. So S is there. If I wanted to use this one, I'm sorry, this is S2. That one up there is download. So this is S4 right here. It's hard to keep this not updating fast enough for me. We've talked about this before, but this is what we call a free running clock. So we learned how we could make a time delay by using, we learned this back in Intro to PLCs, where we could use, set up a time delay or a time pulse by using what we call cascade or interlock timers, right? Where we could come up here and have this timer here, and then we could have this timer here. And if this was timer 4:0 and this was timer 4:1, then I could come over here and use the timer timing, and we could make this thing do what? And this would be T4:1, and this would be T4:0. So what would happen is this guy right here would just constantly do what? Go back and forth and back and forth and back and forth. Y'all remember us doing that one? Well, what we have inside the Allen Bradley PLCs is we have this free running clock that we can use to get a timing reference. It's not as well. Actually, it might be a little more accurate. That we can use instead of using the cross-coupled timers like that. So we're going to bring up the manual and look up the. Oops. So this is the timing. So this is for the 5,500 series or the 1,000. This is the timing for the 1100s and the 1200s and the 1500s, and we have an 1100, right? So what it's saying is if I use my if I use S4 bit 11, then I will get about a half a second pulse on 1100. On the 500, this would be about a what? 20 second, right? You understand that? That's why ours is so slow. So this half second, I could get a half second cycle. This right here would be pretty close to a 1 second cycle. This would be about a 1.5 second cycle. So instead of me using those timing bits, what I can do is I can come over here and I can use that guy, and you can see what it's doing. It's automatically doing what? Going off and on and off and on and off and on and off and on. It's automatically doing that for me. So if I wanted to flash lights or stuff like that, instead of me trying to come up with that cross couple timer, it would be more beneficial for me to do what? So this is it's one contact. If I did it the other way, I would have to do what? I would have to have two timers, and then I'd have to set up, and then I would have to do that cross couple timers. So this is a heck of a lot more efficient than trying to come up with that. Of course, time is not perfect, and then the timers are not perfect anyway. If I wanted perfect timing, then I would use the real time clock. Here, though, so even your timers are not perfect. But I'm using bit 5. We'd have to go back and look at for the 500 series what that time would actually be. But notice it's automatically doing what for me? Yeah, it's automatically. So flashing lights, if I'm going to do flashing lights, if I need just something that flashes lights or ring a bell, yeah, or ring bells or doing here, what we're doing here, it's automatically shifting this thing to the left for me. But what we're doing here is we're shifting a 0 through. And I have it set up. Can y'all see the 0 come see the, yeah. But what we're doing is we're getting our reference bit from the unload bit. So it starts off cleared. And what I'm doing is I'm just rolling so this would be what we call a roll, where I'm just rolling it around, right? You understand what I'm talking about? So notice the light going out. So this would be like a sign where you see it. No, we're using unload. Here, we're starting off with setting all of them to 1. And if I can't clear this out, but when yeah. So originally, when I first started, the unload bit was a 0, and this is my reference bit. So this is what you start rotating in. So this is what the B3. This is the address you're shifting. This is your control bit. This says, okay, where does my bit come from that I'm shifting? Does that make sense? Okay. So if I came up here and put a 1 right here, and then this is a little better than what I'm doing, because here I'm taking the output of this B3 and then I'm sending it to an output using a move instruction. But you can actually see when the 0 comes rolling around. Let's see if we got another one that does. So which one do I have open now? 2. So this will demonstrate this instruction right here a little better. So this instruction right here, can y'all tell what this does? We haven't covered this one yet, but what does it do? Clear. It's going to clear that whole word out, which means it's going to set all the bits to what? 0. Then I'm going to use a time delay here. My time delay, and then the done is automatically reset it. And then my shift bit, I'm going to do a 32-bit shift. And then the information, this is where my bit, this is what I'm actually shifting in right here. So where's my input, where's my shift coming from? Okay, so what do y'all understand? So we're doing a 32-bit shift. And this is 32 bits. Now this first bit over here, this comes from somewhere because we're shifting to the left. That bit comes from somewhere. Well, where am I telling I'm getting that bit from? I'm getting it from input 3. Input 3, Rich, bit 15. Okay. So I'm getting it from this guy right here. So right now, it'll give me a 0, right? Y'all understand that? Okay. So let's download it and see how this one works. Oops, sorry. Oh, it is downloaded. So we're in run. So here we're using, this one is a normally closed. And so we got a master, right? Okay. Oh, I'm sorry. This is a stop. This is backwards. This is the way they do it in Germany. So this is the actual start. Okay. So what do I have in D15 right now? A 0. Okay. And we're sending this. We're not sending this to an output, guys, I don't think. Yeah, we are. Can y'all see what I'm doing? Yes or no? So the bit that I'm shifted to the left comes from what switch? 15. So right now I have a 0. So what's being shifted in? What's being shifted in? 0. Okay. I come over here and set it to a 1. And what am I shifting in now? 1s, right? Okay. Oh, we're only using 3 outputs, by the way. We're actually doing a 32-bit shift. So to see what's going on, we'd have to bring up our B3 register. Yeah, these are the only outputs that we're using. If I come up here and open this up, then what does it do? You can actually see the 0 shift through, right? And we're doing a 32-bit shift. These are the only ones that I've got an output going to right here. I'm shifting a 0 through. And then if I set it to a 1, we're going to start shifting a what through? A 1 through. And that's all the outputs that I'm using. We can go ahead and use more outputs. But, in fact, instead of doing this, what I could just do is I could use the move instruction and just move it into an output port, right? Here we're actually using 3 outputs. So this would sequence start a motor. So this would sequence start motors, right? So here I got 5 motors out here, and then I would come up here. Let's stop it. Okay. So right now I come over here and I click this, and it should come up here and sequence start the motors, right? So now they're starting in sequence. This right here would determine the delay, how much delay so I could adjust this so the motors would get started, right? You understand that? And then, of course, later on I could control this contact, and what would this contact do? So this is going to do what? This is going to sequence stop them, right? You understand that? Does that make sense? So this right here would sequence start them, and then this right here would sequence stop them. And then, of course, hopefully when I hit the stop button, it clears everything out, and it does that, right? Because I'm clearing out that B3 file. Yeah, as long as this right here, when it says that, it is being recorded. Now, is it going to upload? This is chapter 13. No. But you can actually see on the shift left, it does what? Shifts left. Where does it get what the shift left? So this is what's going to come in from the left right here. This bit. Yeah, well, whatever bit I wanted to, I could have used bit. Yeah. So that would be what comes in here into the least significant bit. So here we're using B3, using index address and 33:1, right? Yeah. Which would be B3 file, which would be this guy right here. So we started in right here, and then we're doing a 32-bit shift since I'm using index address, and it automatically goes down to the next word once we get to the link. Okay. The bit address is what you want to bring into this least significant bit right here. So this is what comes into this least significant bit right here. So this would come what comes in here to start off with, right there. And then whatever I bring in, that's what's being what? Shifted to it. So right now, I'm bringing a 0 in, right? Of course, it's not running right now, so it started running. Okay. So what's being shifted in now? A 0, right? Because I've got this switch right here. What do I have coming in from that switch right there? So I've got a 0. So every time it shifts left, it's going to bring what? It's going to bring 15, which is a 0, and it's going to shift it to the left. And then the next time it's going to bring a 0 in there until I do what? Until I close it. And then it's going to change to 1s. And we're doing a 32-bit shift. So using index address, and when it gets to the end of this word, what does it automatically do? It goes to the next. So the index address can actually point it to the next word, right? You understand? So this is the length. So on this, you can use, as long as you've got some place to put it, you can use any length you want to. Yeah, what we would do is we would set the unload bit. So I could do it with 1 bit. I think we've got it in here to start off with. We could set the unload bit and then to a 1, and then bring the bit in from the unload bit. Does that make sense? Yeah. Yeah. So instead of using this right here, I would just use the unload bit to actually bring it back into the least significant bit. And we got one of those programs too. Let's go take a 10-minute break, guys. I know I'm burning out. See y'all's hair smoking out here. So this is the address that you're shifting. Got to be real careful spelling that word, right? This is where your status is going to be held. It's going to be an R6 register, right? Could be an R6 or could be an R13 if we create another data register. This is where the left bit is coming from, or least significant bit. So that's what you're shifting in, right? You understand? And then this is how many bits you're going to shift. This is how many bits you're going to shift. This is actual, it's got a good name. It's actually the length. So this thing is only set up to shift 7 bits. And then if you shift it 8 times, whatever is in the most significant bit will go into the unload bit. So this is the bit shift, and this is the bit shift left. So the file is what data file you are shifting. The control is where it's going to keep the status at. So it's not going to use the status register. We've already run out of status registers, by the way. Your math and all that have used them. So we're going to actually use the data file here for the status. This is where your bit you're shifting in. This is where the least significant bit comes from. And then 7 is the length. How many bits are you going to allow it to shift? And how many bits can you shift? A lot. The most significant would shift into the UL. It'd be R6, right? :0/UL. So we don't have to know the bit number because they've given it a name. And that's the bit shift left. Now let's look at the bit shift right. Control register must be used to hold the status flags information about the bit shift. Okay. So this is the file. This is the address. Is what that's being shifted using index repetition. The bit address is the bit that's shifted into the left. The register is going to the control register. We're using control register. This is where we're going to keep the status at, right? The length would be what? How many bits you want to shift, and the maximum length can be what? 1 to 2048. That's a lot of bits, guys. So let's see how many words would that be. So we'd take that and divide it by 16. That would give us the number of words. 2048 divided by 16. What you got? Divided by 16 because we're shifting words, right? So how many words would that give us? 128 words. That's a lot of words to shift, right? So this is what's stored in the R6 register. So bit 15 would be the enable bit. The enable bit is set to false to true transition of every time the run goes through. The DN bit tells us when we shifted our maximum length, right? You understand that? That would be the done bit. Okay. Then the ER bit, this would tell us that we got an error. It usually indicates that we did what? Such as entering a negative number, right? The error bit would be set. And then the UL bit, this is the unload bit. The unload bit is the instructions output. Avoid using the unload bit when you have an ER error. That makes sense? And this is not in, I shouldn't delete this. This is not in your book. This is in the the actual manual for the PLC. Which you should try to kind of use that as much as you can. Why? For one thing, this book is written specifically. This book is written specifically for the RS Logic 500, and it's written specifically for the 500 series PLCs. So already we're having to modify the book a little bit because we're not using the 500 series. We're using a lot. We're using 1100. Yeah. Okay, so we're changing. We're changing a little bit. You get out there, you get into RS Logic 5000. Y'all understand these manuals are free, right? You understand that? It's just like when we do operation and programming. If you take that robotics class, we don't use the book. We make y'all use the what? The manual. Because if you can understand those things, then you're set for any robot you get to, because those are free, right? You understand? So every book that we got, all those manuals we got, it cost us a dime. The control register, this is actually a data file, right? We could have R6 to R645, but on our PLC, we could actually create more R registers, right? Y'all know how to do that, right? Okay. And that data file, bit shift right. So here what's going to happen on a bit shift right, we're going to get a bit from somewhere, and we're going to shift it into the what? Into the right, and then it's going to move from right to left. So the bit shift left moves from left to right. The bit shift right moves from, I said that word accidentally. Y'all didn't hear that, did you? So here's the bit shift right. So it's got the same thing. So what's B3? This is using index addressing. This is the data file being shift, right? This is our status register for the shift. So this is our flags, right? This is where the bit's coming from, and this is going to be the most significant bit, right? No, this is a shift right. Yeah, it's the most significant bit, yeah. And this is how many bits we want to shift. Now, here, this is the reset instruction. This is inside your counters and your timers. But we can use this reset instruction to reset almost anything. And when we reset it, what's going to happen? It's going to make them all the bits go to zero, right? Okay. So we're moving A into our register. We're going to put this into B3, right? Then we're going to shift B3. Where's our bit coming in on the right? It's coming in from B3:5. And this is the shift right. So let's look at this program. What we got here? So we got a start-stop station, right? You understand? Right now it's stopped. And by the way, like I told y'all, this is common too. Where a motor control, we normally put our stop button on the other side of the down drop, but it's also very popular to put your stop button on the right hand side of the down drop. And this is the way They do it in Germany. Then I'm using input 0 to move AAAA into my destination, which would be that number right there. But I didn't enter it as that number. I entered it in hex, and it converted it to decimal for me, right? I understand that. Yeah. And then I'm moving this into B3:1. I'm moving this AAAA hexadecimal into B3:0. And then here's my 2 shift instructions. So I'm using switch 1 to shift it. And I'm shifting both left and right. We okay? Yeah, so this one, but notice these are using, and what's the length? 1. So what's this thing going to do? Yeah, it's going to shift one time, right? You understand? And then what's the right's going to do? Not one word, 1 bit. Yeah. But when it shifts 1 bit, it's going to take all your so your AAAA will become what? It will shift over. We become 5555 AAA 5555. That makes sense. Yeah, we're going to run it. If my computer don't start doing tasks. I ran into this today. Here we go. Now this is common. I could use another instruction. So when I hit the stop button, what's this instruction right here going to do? Yeah, but what is it going to do? What is it going to do to output word 0? So right off the bat, it's going to clear off the outputs, right? And we can show you all this. So this is this is pretty standard. Like if you got a system that has a reset on it, where you hit reset and you use a move instruction to put all your outputs into whatever condition you want them in for a reset. So we're going to clear them out. So no matter what I'm doing, so let's see what this thing does. Dang it. So this is actually a true PLC program. So I've got 5 set. I'm going to click 4. Okay. And then I'm going to come up here and I'm going to hit my move instruction, which is switch 0, and it calls all my outputs. Now we've only got 6 outputs, guys, so you can't see the full-blown thing of this. So let me bring up my camera. What this thing is going to do, it's going to cause it to jump back and forth. We'll see this. So here's 1. You understand what it's doing? So what it's doing is taking AAAA and shifting it this way. And the next time it's doing what? Shifting it back. And like I said, we've only got 6 outputs on this. If we was actually doing this, it would actually be 16 outputs that were going back and forth. All that programming for nothing. And notice when I come up here and when I hit stop, so right now this is not true, but when I hit the stop button, see what it did to all the outputs? It automatically did what right off the bat? Cleared them. So what we're saying is that if you have like a reset or something like that on your system, you can use a move. And I'll show you all the actual program that I'll show you all the actual next class. I'll show you all the actual program that runs the Festo line over there. And you can see this is exactly what they do when they hit reset. So it's got a reset on it. As soon as we hit reset, it just goes out there and puts those outputs in whatever condition we need them to be in to reset the system and start from scratch, right? Okay, guys, see y'all Wednesday. Oops.